Hello students, welcome to the class. I believe you're all doing good and you're in the best of your health. So till date we have learned about center of mass. After learning so many concepts related to center of mass, let's start the next topic, that is the rotational motion. Now in the rotational motion we'll be seeing what variables we need to consider while a body is rotating. Till now we have seen the linear motion, in that a given object was considered to be a particle which was moving along a linear direction. Sometimes the body was moving along a straight line, sometimes the body was moving in 2 dimension or sometimes in 3 dimension. And we learned that the force acting on the particle or on the body is equal to mass into acceleration. But suppose if we have an object which can rotate about an axis, so how to find out and relate what factors are responsible to give that rotational motion to that body? Example, let me go ahead. Let us say this is an axis, and about this axis I'm going to make a body which can actually rotate. Let me draw an object which can rotate about this axis. Let's say this is a physical pendulum kind of thing, and let's say this object is able to rotate about this axis. Now here you see every particle on this object is in rotational motion, because this object can rotate about this axis as I have shown in this diagram. Now what is the factor which is responsible to rotate the body? Like in linear motion we had force was responsible to give an acceleration to a body along any linear direction. Now for any object to move in rotation we require moment of force, that is a torque is responsible to rotate a body. Now see, at many places we find the application of rotation. Now see, whenever you are going to drive a bike, or let's say you're moving in a car, the wheels of the car are rotating. You can see the ceiling fan in your house, the fan's blades are rotating. Earth is rotating and it is also performing a revolutionary motion on about the center, which is the sun. So simultaneously Earth is said to be rotating also, and it's also revolving all around the sun. So all these examples are typical examples of rotational motion. Let us understand what is that factor which is responsible to give and to provide the rotational or rotatory effect on the object. Now you may see here some variables which we will be using. Let us take an object, and already we have discussed the variables. Here let's say we have a particle of mass m tied with a string and which can rotate about this axis. This particle is able to rotate about this axis. Now as it is rotating, that means in some time it is going to traverse or it is going to be displaced with some angle. So we got that angular variables we are going to use in case of rotational motion. And likewise I told in the concept of circular motion, I have told you all the angular variables that we are going to use, that is the angular displacement, angular acceleration, and time duration in which this will be moving. We'll be having angular velocity of the object. Then what we learned about how to relate the equations of motion that we have learned in the linear motion, how to relate those equations while considering the circular motion. So just I will give you a quick recap and recall the equations that we have done in the case of circular motion. So in the case of linear motion, the equation were like this. Linear equation we had v equals to u plus at, and the case of circular motion we had just this v was replaced with angular velocity, u was replaced by initial angular velocity. Let us replace them, and if we consider the rotational motion, the equations will turn out to be, this will be as it is. I'm going to write the first one will be omega will be equal to omega naught plus alpha t. The second one, s equal to ut plus half at square. This was the second equation. Now here the second equation we have, instead of linear displacement we have angular displacement, that will be given as theta is equal to ut, that will be omega naught t plus half alpha t square. We have this value of angular displacement. Now let's go ahead with the third equation. We have here v square is equal to u square plus 2as. Now instead of v, can we use angular velocity whole square. Then we'll be having square of initial angular velocity is equal to omega square plus 2 alpha theta. Now, there's one more relation. If you remember, I told you V equals to R omega in the circular motion when I was teaching circular motion. So do remember to relate V equals to R omega, and that I'm separately writing here at the center, V equals to R omega and A equals to R alpha. These were certain relations that we have learned already. I was just giving a quick recap of all these variables which we'll be using in the concept of rotational motion also. Now, before starting, if you remember about the Newton's second law that was given as force equal to mass into acceleration, we can relate the same law here in rotational motion also, but using different variables. Likewise, in the case of linear motion, force was responsible to give linear acceleration to an object. Now, what was that thing that the body possessed which was actually resisting any kind of motion to be generated within the object? What I mean to say, that property was called inertia. Because if an object has higher inertia, it will be difficult to accelerate that object. And when I say inertia, I know that the concept that is coming in your mind, you are relating that inertia with respect to mass. And yes, you are right. Higher the mass, it will be more difficult to initiate the acceleration. It will be more difficult to set that body in motion, because for a given magnitude of force, acceleration is given as F by m. Higher the mass, that means lower will be the value of acceleration. Now, in the same way, if higher the mass, it will be more difficult for us even to stop the body, to bring that body at rest. So it's difficult. That means higher the inertia, it will be giving more resistance to you to initiate any change in its state. If it's at rest, it will be difficult for you to accelerate. If it is moving, it will be difficult for you to set it at rest. In this similar way also, here any object which can rotate, any solid object which can rotate, will provide you some inertia so that it will resist its motion, its change of state. If it is at rest, it will be difficult for you to start rotation, and if it is rotating, it will be difficult for you to set it at rest. Now, what is that inertia called in rotational motion? This inertia is known as moment of inertia in case of rotational motion. Let us understand with a particle which can rotate about an axis, and let's understand what will be its inertia. And what we are going to use a term, we use inertia in case of linear motion, and here we'll be using moment of inertia. Now, if you remember, in the case of moment of force, I told you the force should be multiplied with the distance from about which you are going to calculate the moment of that force. In the same way, try to recall that concept and try to relate here when I'm going to explain you about moment of inertia. Say here we have an object. This is the axis. Let's say we have an object of mass small m, and it's a particle. It's a very small object. It's a particle. Consider it's a particle of mass m, and let's say this is the distance r. Let's say this is the axis about which it can rotate. So this is the axis. Now, about this axis, we are interested to find out the moment of inertia of this object. If I give you directly the formula for moment of inertia, you'll be thinking from where it has come. See, the moment of inertia of this point mass is given as I equals to mr square. I equals to mr square, it's a scalar quantity. Remember, it's a scalar quantity, so need not to worry about the direction. There will be no direction of moment of inertia. Now I have given you directly. That means you have to multiply this mass and you have to take its linear distance from the axis of rotation. If it can rotate about this axis, you may see here it can rotate about this axis, so its moment of inertia will be I equals to mr square. Next part, if you're thinking why we call it moment of inertia and how we have got this formula. Actually, it is, if you find its center of mass, if you're going to, because if you recall this concept of center of mass, I have told you center of mass moment about the point, the origin that you have taken, it will be m into x. In this case, it will be m into r. And now if I take the moment of m into r, I'll be having, just multiply r here, so I'll be having this is equal to mr square. This was just a brief description, or you can think it's an explanation why we got mr square. So we are taking moment of mr, that will give us mr square. Now if you are thinking that if we take a solid object, now consider a solid object here. Let's say randomly I have taken a solid object and here I have made an axis. Imagine that this solid object can rotate about this axis. Now there will be several point masses which you can point out within this solid object. We will be having some point mass here, let's say it's m1, some point mass here, let's say m2, some point mass here, let's say m3, some point mass here, let's say m4. Now how can we find the moment of inertia of this entire object? First of all, remember what we have to do. We can simply, because every moment of inertia of any point mass is a scalar quantity, so distance of this, let's say from the axis it's r1, for m2 let's say it's r2. See, I'm taking the linear distance because from x it's actually two-dimensional object which, and the axis is like this. You have to understand that this is the axis and the object is like this. It can rotate in this way. So any point mass, the distance I am showing in this way. Now for this mass m3, we have this distance from the axis as r3, and we have for mass m4 will be having r4. Now if we try to find out the net moment of inertia of this object, we have to individually add all the moment of inertia of all each the particle, and the method is very simple because this is point mass which is distributed all within the body which has been shown here. So we have to use the concept of integration. Now see, if I take only one mass and its mass is m1, so moment of inertia I1 will be equal to m1 r1 square. Moment of inertia I2 for the second mass, it will be m2 r2 square, and so on. We'll be having In, that will be equal to mn rn whole square. So net moment of inertia we can write this is equal to I1 plus I2 plus I3 and so on plus In. So what is this? This is just simply you have to add m1 r1 square plus m2 r2 square. And so on, you will be finally adding mn rn whole square. Hope you can see till here, that will be very much clear to you all. So if you have discrete object system, such point masses located in space, some here, 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 and you are having the distance given with respect to the axis, you have to just simply take square of the distance multiplied with the point mass, you will be getting moment of inertia of that point object. And you just take the summation, you will be having this, just add all of them, you will be having this formula. So in short, we can write that as sigma mr square, but here I have drawn a continuous body. So generally you will be required to find out moment of inertia of continuous objects. It's very simple. If we take at any point at a distance r a small mass dm, so how can we write the moment of inertia? That will be given as, for the moment of inertia of this small moment of inertia of this small object will be given as dm r square. In simple words, we can write this as r square dm. Now for the moment of inertia of the entire object, of this entire system, you have to add small moment of inertia, and when the object is continuous, we cannot do summation. The summation will be replaced by integration. So moment of inertia will be nothing but integrate di, such small moment of inertia, that will give you integration of r square dm. This is basically the moment of inertia of any continuous object. So I want you all just make a note in your copy if you want to understand how to find out the moment of inertia. So moment of inertia general formula is I equals to integration of r square dm. And one more, if you have discrete object system, you have to write that as m1r square plus m2r2 square plus m3r3 square and so on. So I want you all just take down till here. I'll start from here. So okay, after learning the concept of moment of inertia of several objects, let us write down separately whenever we'll be having discrete object system or continuous object system. So how we are going to find out the moment of inertia. So let's write down the moment of inertia of discrete object system. Of discrete object. When I say discrete object, it means we have several point masses which would be located in space of discrete object system. Now see here, there will be an axis about which all these objects can rotate, and let me show you. This is the axis, and we have several objects. Let's say we have an object m1 whose mass is, let's say, 2 kg, and it is at a distance of, let's say, 20 centimeter. And then we have one mass m2 which is of 1 kg, and it is at a distance of, let's say, 10 centimeter from this axis. And we will take only one more mass. Let's say we have m3, that is again, let's say, 3 kg, and its distance, let's again take as 20 centimeter. So we have been provided each of the particles. These are individual particles. This is the axis about which they can rotate. So we are required to find out the moment of inertia of this 3 particle system about this axis. So as I told you, if you have particles, just simply take the moment of inertia of each of the particle and add them, because moment of inertia is a scalar quantity, so directly you can add them. So we'll be using the formula. The formula will be, this will be m1 r1 square plus m2 r2 square plus m3 r3 whole square. So m1 will be what? It is given as 2 kg and 20 centimeter. So we'll be having 2 kg and 20 centimeter. Let's use this as 20 centimeter only, and later on we will take in meters. We'll write the 10 to power minus 4, that will be given in square meter. m2 is actually 1 kg and distance is 10 centimeter whole square, plus m3 is again 3 kg and distance is 20 centimeter whole square. And since we have each time we have written centimeter whole square, let's write here 10 to power minus 4. So we will be having the final value of moment of inertia in SI units. Now moment of inertia will be having a unit because it's a product of mass into square of distance. Its unit will be kg square meter. So let me mark here the unit as kg square meter. Go ahead. 2 and 20 whole square will give you 400, 400 to 800 plus 100, 400 into 3, that will give you 1200 multiplied by 10 to power minus 4 kg meter square. We have obtained this, the value of moment of inertia. This will give you 800 plus 1, 900, 1200 plus 900, 2100, or we can write 2100. So we can write 2.1 and into 10, we can write 2.1, yes, and into 10 to power minus 1 kg meter square. This will be the value of moment of inertia of this 3 particle system which have masses given as this and the distance from the axis as it is given. This was for discrete object system. Generally we will be having continuous objects whose mass will be maybe uniformly distributed or maybe given, whose distribution may be given related to the distance with respect to the axis. Now in this case, if you see, one point of difference in the case of inertia, while you are evaluating the case of linear motion, that was directly equal to mass. There was no role played by the origin or by axis or by the straight line, nothing was that. The mass, if it is 4 kg, that will be the inertia of the object in the case of linear motion. But here 2 things you need to take down. First of all, moment of inertia depends upon both mass of the object and it is also dependent upon the distance from the axis about which the object is rotating. Because final formula for the moment of inertia is mr square. It is having both the variables mass and r square, that means distance from the axis. Now if mass is higher, that means moment of inertia is going to increase, no doubt. And if distance from the axis is higher, that means again moment of inertia will be higher, because that is directly proportional to the square of distance from the axis of rotation. So it depended on two things, mass also and distance from the axis of rotation. So if higher the moment of inertia, it will be more difficult for you to set it in motion if it is at rest, and if it is higher the moment of inertia, it will be difficult for you to bring it at rest if it's in motion. Understand the concept of moment of inertia directly. It is providing an inertia, it is providing a resistance while actually to initiate any rotational motion in the object. Now let's go ahead and understand the method to evaluate the moment of inertia of continuous objects. Now we learned about moment of inertia of discrete object system. I have already given you the idea of continuous objects. Continuous objects, it means the masses will be distributed within the entire area or the volume of the object. You may see here we have, like say this is the object, and let's say this is the axis. This is the center about which it can pass. Now this object can rotate. There will be several point masses within the object. As I told you just now, the moment of inertia will be evaluated using the concept of integration, and moment of inertia is nothing but it's given by I equals to r squared dm. So what is the idea behind calculating this moment of inertia? You have to take any point mass within the solid object and then check its distance from the axis, and then you apply this integration formula. That will be the method which we will be using to find out moment of inertia of continuous objects. Let's go ahead with the very simple example of finding the moment of inertia of a uniform circular ring. Let's go ahead and do the first one, moment of inertia. Let me write moment of inertia as mi. This I will be using in short mi, so I may not write the entire expanded word. Moment of inertia mi, moment of inertia of uniform circular ring of radius r and mass m. Uniform circular ring. Whenever I am writing this, it means you can automatically take that mass will be capital M and radius will be capital R. So we have this as the value moment of inertia of uniform circular ring. Now how this ring will be rotating? Let's say this is the axis, and let's say we have this as the ring. I have not shown dotted, but okay, imagine in this way. Imagine that this is a ring and its radius is given as r. Now it can rotate. Let me draw its axis also. It can rotate. Now how to find out the moment of inertia? As I told you, we have to imagine a small particle within the object. Let me imagine this point mass dm, and it is a distance of capital R from this axis. That's quite simple for us to imagine. Now the moment of inertia of this entire ring about this axis will be given as integration of r squared dm. I am writing why capital R, because capital R is the distance of this object, small particle whose mass is dm, so r squared dm. Let's now see, if we are going to write dm over the entire periphery of the ring, that is over the entire perimeter of the ring or the entire circumference of the ring, we will be, every time when dm is varying, r will be same. So r can be taken constant, it can be brought outside of the integration will be having this. Now integrate dm, you will be having total mass of the ring, that is capital M, so mr square. So moment of inertia of a uniform circular ring is nothing but mr square. That's quite simple. Quite in this very simple way we got this first derivation. Let's go ahead with the second one. And regularly in every class I tell you to remember these simple formulae which I am telling you. Here we have started with learning moment of inertia of uniform circular ring. So you should always remember this. The formula will be I equals to mr square. So do remember this. Second one, the second derivation. After doing the derivation for a ring, let us derive the formula for a disk. What if we have a disk? So moment of inertia of a uniform disk. Again, the variables used will be mass capital M, as regularly we use it, and radius capital R. Generally, where you find disk, you would have seen your DVD player or your CD player. In that, the disk is circular in shape and that revolves. Now if it revolves, that means if the disk is light, it will be very easy for you to rotate also, and if the disk is heavy, it will be difficult for you to rotate the disk. That means mass has got some role to play, and I also told you the axis has also had got the role to play while finding the value of moment of inertia. Let's see how the radius and mass is dependent while we are evaluating the moment of inertia. You see here, let's say this is the disk. See, I have drawn it in oval shape because actually I am trying to depict in the plane which is perpendicular to the plane of the board. So that's why I have drawn in oval shape. I am not drawing in a perfect circular shape. Its mass is capital M, its radius is R. If you are thinking where to take the elemental or elementary particle, you cannot take any point mass here. That will be difficult for you while you are integrating. So what do? Take any elemental ring here whose radius is given as R, and let's say whose width is given as dr. This is the elemental ring which we have taken. Its width is given as dr, so let me mark separately. This is the width which I am marking, and this width is given as dr. Now what will be the mass of this elemental angular strip that we have taken? So let me write it separately. Mass of elemental strip that we have taken. I believe that if you have learned all the derivation in the case of center of mass, so already you must be knowing the method that should be used here. Mass of elemental circular ring. Elemental circular ring that we have considered. Now total mass is given as capital M. The radius of the disk is given as capital R. So can we write this? Total mass upon total area will be given as M upon pi r square. Now we multiply it with the area of the shaded portion. We will obtain this. Now area of shaded portion, its circumference will be 2 pi r. Multiply with the width dr, you will be having the area of the shaded portion. So you will be having this as 2 pi small r dr. Now we have to integrate this entire circular strip when it is near the axis and when it is at the periphery of the disk. When I say periphery, that means I am talking about the extreme perimeter of the extreme edges of the disk. Now you see here, when r is equal to 0, then we have this circular strip will be here, coinciding with the axis, and when r equals to capital R, this entire circular strip will be coinciding with the extreme periphery of the disk. So we have to vary r from 0 to capital R so that you can cover the entire disk. Pi and pi cancelled out, will be having this mass dm of the circular strip that comes out to be 2 mr dr upon r square. This is what we have obtained. Now, integration we have to do to find out the moment of inertia of the entire object. So, the moment of inertia is given as r square dm. Now, see, I will start with writing this way. Now, what is the moment of inertia of this elemental circular strip? Its moment of inertia, we know that a circular ring has a moment of inertia mr square. So, its moment of inertia will be dmr square. So, let me integrate this dmr square for this entire disk. We will be having I equals to integrate r square, and dm will be given in this way. Then you put up the value of dm and vary r from 0 to capital R, and dm will be 2 mr dr upon r square. You see here r square and r will be having r cube. So, r cube, if you integrate, you will be getting r power 4 by 4. So, I am writing 2m, the constants outside, and here I am writing the r cube integration as r to the power 4 by 4 from 0 to capital R. Just do the next step of calculation. You will be obtaining this as mr square by 2, which can be written as half mr square. So, this is the value of moment of inertia of a uniform disk. That is quite easy to reach to this value that we have got, and I want you all to by heart this half mr square, that is the moment of inertia of a uniform disk. Please take down till here and start from here. Now, with these two examples, you would have learned how we are deriving the moment of inertia of these continuous objects. Let's go ahead and let's learn more moment of inertia for some more objects. And next, we are going to do a simple object, and that is a rod of mass m and length L. So, let's write down, let's note the moment of inertia of uniform rod. Uniform rod. So, if I say uniform rod, so you can take the variables on your own. Let's say its mass is m, length is L. Axis I will be showing you within the diagram. Now, say two axes you can consider. First axis will be when the rod is hinged at one of its end. That is, if the rod is hinged at one of its end, it will be somewhat in this way. Its mass is m, its length is L. How to find out the moment of inertia of this system? So, as I told you, recall the basic steps. Take a point mass, find its moment of inertia, that will be the small moment of inertia of that elementary particle, and then you integrate accordingly. Let's say we have taken a point mass here, and this is at a distance of, let's say, x, and let's say its width is given as dx. So, we will be having its small mass that will be actually dependent upon this mass and length L. See how we are going to get it. What will the mass of this elemental part? Let us write it separately. Mass of elementary particle. Mass of elementary particle, that will be quite small, dm. Can we write this as total mass per unit length multiplied by dx? That's quite simple. Now, see here, this is the axis. This is the axis. Let me show you in axis form. This is the axis about which this rod can rotate. This can rotate about this axis. Now, how to find the moment of inertia? The moment of inertia of the elementary particle shown, this will be given as mr square, so we are using dm x square or x square dm, and moment of inertia of the entire rod will be given as x square dm. Substitute the value of m, dm in terms of dx. So you will be having, and vary x from 0 to L. When x is 0, it will be lying at this end, this elementary particle. When x is equal to capital L, this particle will be lying at this end. Do it, you will be having integration of 0 to L x square dm m by L dx. We got this. Now perform the integration. See, m by L can be taken outside, that's constant. You can take it outside, we'll be having m by L. Integrate x square dx, will get x cube by 3. X cube by 3 from 0 to L. Let me write a bit larger. Then what we are going to have? We are going to have L cube by 3 minus 0, and L is here, so we will be having 1 by 3 ml square. So moment of inertia of this rod comes out to be I equals to 1 by 3 ml square, and I want you all to note down and by heart this. I equals to 1 by 3 ml square. This is required when the axis is hinged, when the rod is hinged at one of its end. Now what if we change the axis? If we change the axis, we bring the axis passing through the perpendicular bisector of the rod. Let's finish it very fast. When the axis is not at one of its ends, rather it is passing through the perpendicular bisector of the rod. This is the scenario. This is the axis this time. Now the rod can rotate in this way. You can imagine rod can rotate in this way. Again, it has got same mass m and length L. So its mass is m, length is L. The method used should be the same. That is, take a small elementary particle at a distance quite obvious, let's say x, and its width, let's say we have taken as dx. So rest of things I want you all to note down already, because rest of things are written here. Mass of elementary particle will be m by L dx. Now moment of inertia of this with respect to the axis shown, it will be dm x square. Then moment of inertia, total moment of inertia will be just integrated. Now only things we have to change the limits. See here, now the limits will be, because the entire length is L, the limits x should vary from minus L by 2 to plus L by 2. So let us substitute here minus L by 2 to plus L by 2. This will help us in finding the value of moment of inertia, x square dm. So minus L by 2 to plus L by 2, x square dm is m by L dx. Go ahead and integrate it. You will be obtaining, integrate, I hope that it's visible till here, and you can easily, I am writing plus L by 2 at this end. Don't worry, minus L by 2 is written here, L by 2 is written here, but that means lower limit and upper limit. X square, and now I should write directly the integration value. That should be equal to, take m by L outside, and it will be x cube by 3. Writing at the bottom end of the board is quite difficult. X cube by 3, and here minus L by 2 to plus L by 2. Substitute the limits, you will get the required answer. Here can you take ml by 3 and substitute the limits, you will be having, we will be having L cube by 8, and here we will be having minus L cube by 8. See what we are going to get. We will be obtaining this as ml by 3 m by 3l. Substitute the upper limit, will be having L cube by 8 minus L cube by 8. This you are going to obtain L cube by 8 plus L cube by 8 will give you L cube by 4. So ml cube upon 3l, and let me write it separately so that you don't get confused. M by 3l multiplied by L cube by 4. Now very simply you have obtained this as 1 by 12 ml square. This is the value of moment of inertia when the axis passes through the perpendicular bisector of the rod, that is through the center of the rod. So this is 1 by 12 ml square. So after doing such moment of inertia and evaluating the value of moment of inertia of all these continuous objects, I hope you have got the idea of how to evaluate the moment of inertia. In the next class we will proceed from here. Till the time, do revise the concept of moment of inertia and do check this simple derivation. I'll meet you in the next class. Till the time, wish you all the very best. Take good care of yourself. Meet you in the next class. Thank you everyone. Bye bye.